So we know a handful of information about gradients, and so with this one more fact, we'll kind of round off this whole our whole collection of properties, and then be able to put all the properties together with maybe some examples and stuff. So one more fact about gradients. I'll start off by looking at a generic, you know my generic function? I'm not going to draw that. What? The sheet. So that sheet is a function where we would say z is equal to f of x, right? So I'm more interested in an implicit function. And do you remember what implicit was? An ellipsoid is an example. An implicit function is a function where all the x, y's, and z's are together. We can set this equal to 0 or equal to a constant. It doesn't matter. If it's equal to a constant, just bring the constant over to the other side so it's set equal to 0. It might be better to think about it that way. But this can describe a surface but not only is it a surface, but we can think about this as a level surface. Remember we talked about level surfaces? So it's a level surface of the function f of x, y, z. Yeah? Is a. So remember that this, as a relation of x, y, z, and w, can be visualized or pretend to visualize something in 4 dimensions. But if we look at level sets or level surfaces by setting w equal a constant, we're cutting it with some w is equal to a constant, w is equal to 1 plane, or w is equal to 2 plane. I guess we won't call it plane, but we call it a space. Something that 3-dimensionally cuts this 4-dimensional figure, we're going to get a 3-dimensional surface. So an example of this is an ellipsoid, x squared plus y, or a sphere, x squared plus y squared plus z squared is equal to 1, for example, is an example of a level set. Okay? So it's a level surface of something. So we're going to attempt to extract the gradient from somewhere here. And the way we're going to do that is we're going to create some random curve. So first, let's let x naught, y naught, and z naught be on the surface. And we're also going to let r of t be some curve on the surface. And we want the curve to be passing through the point x naught, y naught, z naught. And just for simplicity's sake, we'll let it pass through at t is equal to 0. That part doesn't really matter, but we'll assume that. So the surface is some 3-dimensional surface. It doesn't have to follow the function rule, so it could not pass the vertical line test, and that's still okay, because that's how you would tell if it's a function or not, right? Vertical line test. But we'll allow it to not bother having to go through that criteria. And then we'll say that this curve R of t is just some curve on the surface. And then let's say this is our point x naught, y naught, z naught. And if you want to keep it simple, draw an ellipse. But we'll see this as an example where we'll draw an ellipse. But I want to keep this general. Okay? So remember that this is a surface that we're talking about. This is f of x, y, z equal to 0, or a constant. Doesn't matter. But it's a level curve, level set of that four-dimensional function. And R of t is a space curve, is a curve that's on the surface, so it's a three-dimensional curve. It has x naught, it has x of t, y of t, and z of t. Okay? So what we're going to do, since we have already talked about the chain rule, is we're going to compose these two functions. So we'll consider f of R of t. Now, f of R of t, when you put R of t inside of the f function, that means it's going to be on the surface because that's how we created it. And if it's on that surface, then that means when you put any point on this curve is a point on that surface, so any point on that surface when put into this function is going to give us 0. Does that make sense? So any point on this curve is going to be given by R of something, right? So regardless of what t is, R of anything, R of t is going to be on this surface. Now if it's on the surface, when we put those x and y and z values in from R, when we put that into the function f, we're going to get 0 because it's on that surface. If we get something else aside from 0, then that means we jumped out of the surface. But that's not how we define the surface. We define the surface to be, that's not how we define the curve. We define the curve to be on the surface, so it's never going to jump out. So this is always going to be equal to 0. Now guess what we're going to do? We're going to take the derivative. So the derivative of this, we could do this in pieces again, and then I'll say, oh, doesn't that look like a dot product? Should we do that? Okay. So we'll go fx, and then the first component of R of t is, let's say, fx of R of t. Times x prime of t. So R of t is x of t, y of t, z of t, plus this derivative of f with respect to y evaluated at R of t times y prime of t, plus the derivative of f with respect to z evaluated at R of t times z prime of t. So we took the derivative of the left-hand side, the derivative of 0, or if it was a constant, is equal to 0. Hey, look, doesn't this look like a dot product? Right. So if we peel this apart as a dot product of two vectors, the first vector would be fx, fy, and fz. The second vector would be x prime, y prime, and z prime. And their dot product is equal to 0. And then you say, hey, wait, look at this. This is really what? What is this first vector?
Gradient.
This is the gradient of f evaluated at r of t. Dotted, hey, what's the second vector?
R prime.
This is r prime of t is equal to 0. And you know that when the dot product's equal to 0, that they are perpendicular. These two vectors are perpendicular. So the gradient is perpendicular to a tangent vector.
Didn't we do that last time?
We did it for 2 dimensions. Now we're doing it for 3 dimensions. The gradient is perpendicular to the tangent. I mean, we could put 0 in for t, right? So if t is equal to 0, we have r of t is x naught, y naught, z naught, or r of 0 is x naught, y naught, z naught. So the gradient of f at x naught, y naught, z naught is perpendicular. This is a tangent curve. And if it's perpendicular to a tangent curve, and this is some arbitrary tangent curve, so we have a tangent curve over here, and the gradient is perpendicular to that. And then what if we had a different tangent curve? Since this curve is arbitrary, what if we had a different curve, and then we'll have another tangent curve, and that's going to be perpendicular to that as well. The gradient is going to be perpendicular to that as well. So we could safely say that the gradient is perpendicular to a level surface. How is this different from what we did yesterday? Yesterday, as Brian said, the gradient is perpendicular to a level curve. I should have had this ready. One of the 2 facts that we came up with yesterday, gradient vector is perpendicular to a level curve. So that's a gradient for a function in 2 dimensions, a function of 2 variables, right? So, I mean, really what we're looking at is a 3-dimensional figure. But when we look at the gradient, it's going to be the same dimension as your domain, which is, in this case, 2-dimensional. Your domain is xy. So your gradient is a 2-dimensional vector that's perpendicular to a level curve in 2 dimensions. That's what we did yesterday. So today, we're saying that the gradient is perpendicular to a level surface when your function takes a 3-dimensional input as your domain. Then we can take a look at that as a level surface, and then we can find the gradient. Yes? We could make one. Yeah.
By level surface, do you mean like the tangent plane? Like, what do you mean by level surface?
If it was a circle,
What?
if it was a circle, the gradient would always be pointing towards the center.
It depends. Yes.
Go Ryan.
That's because he watched that video on four-dimensional stuff. Ryan said, a level, what did you say? A level curve is a slice of a surface, a three-dimensional surface, when you slice it with a plane, and then you see a level curve, like contour maps. A level surface is a four-dimensional function that's been sliced with a plane or a space, and then you get a surface. Okay? Now, we don't necessarily have to think of it as a four-dimensional space. We could just identify it as a surface with x, y, and z all together. Okay? I feel like you guys want me to do an example. Are you guys using this? I'm using this because I'm encouraging you guys to visualize things. Now, if you guys aren't going to use this, I'm just going to go back to the easy ones, which is, for me, Graphic Calculator and Mathematica. Right. Are you guys going to use this? All right, fine. It's free, right? That's why I'm starting to encourage this, because the other stuff is not free. So the first thing we want to do is, first thing I would like to do is to come up with a level surface. And one of those popular level surfaces would be ellipsoids or whatever. So example, x squared minus 4 plus y squared, x squared divided by 4, y squared over 25 plus z squared is equal to 1. Okay? I can bring the 1 over to the other side, but when we take derivatives, it's going to disappear, so I'm not really going to care about that. So what I could do is I could say that my function, my four-dimensional function, is equal to x squared over 4 plus y squared over 25 plus z squared. And then, like I said, I can put a minus 1 here or leave that alone, because when I take the gradient, partial derivatives, that 1 will disappear anyways. Now, I need a point. If I'm coming up with this problem, I need a point that would satisfy the x, y, and z being on this ellipsoid. I could put 0, 0, 1, but that might be too easy. So let's see if we can come up with, I don't know. Can somebody come up with a point? How about if we put 1 here and 1 here, and then figure out what the y is? 3? I can't just random. I have to. It has to work for this.
Negative. Oh no. It's squared.
It's squared, so that just means there's positive or negative. I could choose whichever one I want. All right, fine. 1/4 plus y squared over 25 plus 1 is equal to 1. So y squared is equal to negative. Wait. I can't have a 1 there. Crap. Okay. This one? Is that going to help? All right, we're changing the problem. 16 we want? Okay, why don't we just leave it blank? I mean, not leave it blank, but just say y squared. All right, now are we any closer to finding a point? Put a 1. One half and 0. That's not very interesting. Yeah, it's not going to be interesting because this is going to be like vertical plane or something, or horizontal plane. But that's fine. I suppose we could just look at the book, right, and find a problem in the book. Should we start over and look at the problem? Look at the book. Sorry, I'm just wasting time now. All right, so any of these 41 through 46? You can see that they have the point there already, which makes it nice for us. 46 maybe? Let's do 46. So as you can see, this has an x, y, z relationship where we can't easily solve for one of the variables. So we can't treat it like an explicit function. We have to treat it like it's an implicit function. And this could be seen as a level surface of some sort if we bring everything over to the other side. So that's going to be our first step, is to bring everything over to the other side and pretend like that is your capital F function, a function of x, y, and z. So x to the fourth plus y to the fourth plus z to the fourth minus, if we bring everything to the left side, 3x squared, y squared, z squared. And then this would be set equal to 0 then. So now this is officially a surface of a level surface of this complicated looking function. And just to make sure, if we put 1, 1, and 1 in for x, y, and z, we should get this whole thing to equal to 0. Okay? So, let's pull out the graphing calculator or the graphing program. And for this, this is a relationship, an implicit relationship between x, y, and z. So I can't use one of these z is equal to functions. So I'm going to unclick it. Boy, they shrunk it down, huh? So I unclicked it, and I'm going to look at the graph, and I want to graph an implicit surface. So this allows me to create an equation with x, y's, and z's in it, and then it'll graph it to me. It'll graph it for me like an implicit surface. So it's x to the fourth plus y to the fourth plus z to the fourth. And I can write it the way it's written in the problem, where it's equal to 3x squared, y squared, z squared, or I can say minus 3x squared, y squared, z squared is equal to 0, and it would be the same thing. So I'll write it the way, because we have that option here, I'll write it the way they have it written. I'll worry about this a little bit later in case I need to worry about this number of cubes in each direction allows me to refine it more. So the higher the number is, the smoother it's going to look. But let's not worry too much about that. So given this, I might be interested in zooming out a little bit more to see if I see more. Maybe I see a bunch of spheres in there. This is just for, oops. All right. Well, you can play around with that and see what you get. But this is, in general, this is what we have. Now, I don't know how easy this is going to be to visualize, especially seeing it through the projection. But I can also throw in the point that I'm looking for. I'm looking for a point, and the point is 1, 1, 1. Boy, too many options here. Yeah. There it goes. You see it? I wonder if you can make this transparent. Wow. All right, I don't know if you can make it transparent. So this is it. We have that point over here from this point of view. Can we undo the box? What? Make surface transparent. No. Helped a little bit. Okay, so this is our graph. Now, we might be interested in, I can't just hide this, I just have to get rid of it. We might be interested in finding the equation of the plane here, or the normal line. Plane, normal line. So both of those require a point and some sort of direction or a normal vector, right? So let's talk about what should we do first, line or plane? Line, let's do the line first. Okay, the key word here is we want a line. We want a point and direction. And if this is the normal line, the direction will be the normal vector. Okay? We have the point. Now we need the normal vector. So with this new knowledge that we have about the gradient is perpendicular to a level curve, and this is a level curve or level surface. Gradient is perpendicular to a level surface, and this is a level surface. We should be able to use the gradient to find our normal vector. So let's find the gradient of this. So the gradient of f will have three components. There will be the derivative of, this is my f function over here, right? Because I had to bring this over to the other side. So this is my function. The derivative with respect to x, 4x cubed minus 3 x, wait. So the x, the yz is constant, so the 2 comes down. That will be 6x to the first power y squared z squared. So that's a derivative with respect to x. With respect to y and with respect to z are going to be pretty similar. So the partial with respect to y is 4y cubed minus 6x squared y z squared, and then finally 4z squared or z cubed minus 6x squared y squared z. That 2 from the z came down. All right, and since I am focused at this point, 1, 1, 1, I would be interested in finding out that gradient evaluated at 1, 1, 1. So I'm going to put 1 in for x, 1 in for y, and 1 in for z. So if I put 1 in for x, looks like I'm going to get negative 2. And similarly for the rest of them, right? You can scale this down to 1, 1, 1, or negative 1, negative 1, negative 1, because all we want is the direction. We don't really care about the magnitude of this vector. I'll leave it like that. So we found the direction, and then we have the point. So the equation of the line, we'll call it L of t, is equal to the point plus t times the direction and you have an equation of the line. So this is called a normal line because it's perpendicular to the surface. Good? Questions? What do we need it for? What? If you want to find the equation of a normal line.
You want to like burrow yourself down to the center of the earth.
Yeah. Let's say you're describing somebody as a surface and you want to stick a skewer that's perpendicular to that surface several times. And then you'll have the equation of that line. Since we have the graphing ability to graph lines as well, let's do that. Let's go back to our graph and graph that line by adding a space curve, because the line is really just a space curve. And I wrote it in vector form, but we can write it in parametric form. So this is going to be 1 minus 2t. 1 minus 2t and 1 minus 2t. Our t can go from whatever to whatever. Negative 10 to 10 sounds fine. And let's go ahead and graph that. And we see, if we use primary colors, you see that that surface got stabbed by that line perpendicularly. Okay? So now let's find the equation of the tangent plane. That's kind of cool, huh? All right, so we'll take this information and then we'll do the tangent plane. And we'll remember that our normal vector is negative 2, negative 2, negative 2. All right, so we have a point and we have a normal vector. So for a tangent plane, we need a point and a normal vector. And you remember how to construct this?
Yeah.
All right, so the normal vector are just coefficients of the x, y, and z. Minus 2x, minus 2y, minus 2z. And then the d that we got is a dot product between these points, the point and the normal vector. So that would be minus 2 plus minus 2 plus minus 2. And if you simplify this, you'll see that had you used 1, 1, 1 here, you would have gotten the exact same equation, right? So by that I mean if you factor out a negative 2 and then cancel both sides by negative 2, you have x plus y plus z is equal to 3. And if you would have made this 1, 1, 1 instead of negative 2, negative 2, negative 2, you would have gotten the same answer. Okay? We can also think of this as z is equal to 3 minus x minus y if you want. But since it's a plane like that, if we write it like that as a function in the graphing program, you can just type it like that, right? So 3 minus x minus y is equal to z. There's your tangent plane. Is that a good picture, or like that? Like this? This? So, there you go. You can find equation of the tangent plane. And we found it using the gradient, because the gradient is perpendicular to the level surface. Is this cool or what? Now, I want to make another connection. I don't know if I want to do this. Let's try it. See what you guys think. Sorry. So you know our old friend, this surface? It doesn't have to be the surface, doesn't matter. What matters is that this is a function now. Do you remember the slope, or do you remember the tangent line or the tangent plane? Let me ask that again. Do you remember how to find the equation of the plane tangent to the surface at the point x naught, y naught? Okay? Let's just say that you remember. If I look at this equation and I fiddle with it a little bit, and by fiddling I mean bring the z over to the other side, what do I have? I essentially have a surface, right? Or wait, I essentially have a level surface, right? Because you got a relation between x, y, and z. Z just happens to be on its own that you can solve for, which can look like a function. But if I bring it over to the other side, it looks like a relation of x, y, and z together equal to a constant, this is 0. So it looks like a level surface. And we know, if we think about this as a relation between x, y, and z, and we look at this as a level surface, we just talked about how to find the tangent plane. And how did we find the tangent plane? We found the gradient of f, right? The gradient of f is a derivative of this whole thing with respect to x. What is the derivative of this whole thing with respect to x? Well, there's an fx here somewhere, but this has no x's. The derivative with respect to y, there's a fy here somewhere, but there are no y's in the z. What's the derivative with respect to z? Just -1. Yeah?
Isn't z a function of f and x and y though?
Z is a function of x and y, but when we bring it over to the other side and treat it like it's an independent variable, then it just becomes an independent variable. We're bringing this up to the fourth dimension. So if it goes up in the fourth dimension, it just becomes like one of the other kids. What? We have the gradient. This is our normal vector, right? We have a point. Wait, that's a two-dimensional point. Oh, you guys know what the third dimension, right, is, right? So the point is x naught, y naught, and z naught, which is also f of x naught, y naught. So there you go. Point, blah, blah, blah. So let's say we evaluate this as x naught and y naught. This is f sub x evaluated at x naught, y naught times x minus f sub y evaluated at x naught, y naught times y plus, this is a minus 1 times z. That's the coefficients, right? Is equal to, now I have to take the dot product of the vector and the point. And I'm putting this as one whole thing. This is fx evaluated at x naught, y naught. That's what I mean by that. It's not two things that are multiplied. It's just one thing. Yeah?
Wouldn't it be x minus x naught? Oh no, you're using it for the other side. Okay.
Yeah, so the other side, I'll get fx evaluated at x naught, y naught times x naught. You see it? Plus fy evaluate x naught, y naught times y naught and minus f of x naught, y naught. This is this would be like the gradient at that point. So I guess AJ was referring to the actual formula that you guys were using that Renee and Alex presented the other day. And that is to, if we bring this term over to the other side, we have our fx evaluated x naught, y naught times x minus x naught. That's x naught that was brought over from the other side. And then we'll take these two terms with fy, bring that over. How about the z? What are we going to do about the z? I know what. Let's bring this over to the other side. And so it would be plus f of x naught, y naught. And then let's bring this over to the other side. So it would be a positive z. So that's exactly the same formula that they gave you guys the other time. It is a linear approximation, right? It's the f of x naught, and then you have the derivative, x minus x naught, and then the derivative of the y minus y naught. So that's what it is. The plane is essentially a linear approximation. What you're doing is you're taking a complicated surface like this, a complicated function, and then you're using planes, because plane is a linear function. You're using planes to approximate it. Wow, that's cool. Now you guys know everything about gradients. Almost everything. except for that one problem that's going to be on the test.
You saw our scores in the mock.
I'm encouraging you to talk to Courtney, find a tutor, talk about it with your classmates, meet somebody, say, hey, let's go study over spring break, because I have a set of notes that I made a while ago that summarizes directional derivatives and gradients in 2 pages. And there are no examples here. There are just formulas to put these things together. So I will make this available for you to download, but I think it's worth going over. So let's take a quick look at this information. And I wasn't going to take pictures because I was going to just have you guys do it. But I'll take pictures so I can annotate or whatever, highlight. Yeah?
That last example you used to do, can you summarize the words exactly what we did there?
Well, this wasn't quite an example. This is an explanation of another property. But I can do an example.
Well, what is the property?
The property is that if you have this function here, that it's a function of 2 variables, the gradient is only a 2-dimensional vector. Okay? But if I'm interested, so I know that the gradient is going to be perpendicular to a level curve, so if I had a level curve down here, my gradient would be a 2-dimensional vector that's perpendicular to that. But if I'm interested in finding the tangent plane, I would need a 3-dimensional vector, right? So the 3-dimensional vector. The 3-dimensional vector is going to be, the first 2 components will be the gradient, and then the third component is -1. Yeah? Uh-huh. No.
On a level, on a curve, isn't it the normal is the one that's pointing in, it's the normal vector, but then if you have a surface, it's the one, like, if you have a surface like this, it's curved like this.
Yeah, so I think in 3 dimensions, we have to look at this in 3 dimensions. Your vector would be going like this, and your binormal is perpendicular to the tangent plane. Your tangent vector is a tangent vector, and your normal vector is up a little bit, and it won't be flat like a gradient. So, not necessarily. But that's a good observation. All right, so Ryan, does that make sense? So it's because this is a 2-dimensional input, our gradient is 2-dimensional, but we might be interested in a tangent plane, which is a 3-dimensional vector, and so that third dimension is going to be -1. Okay. Well, that -1, what, this -1? That -1 is what we got when we took the derivative of this new function over here, where we put the x, y's, and the z's all on one side. When we took the derivative of this with respect to z, and we took the derivative of that with respect to z, we got -1. Yeah. Oh, we need to come up with a problem first. Well, let's take a look at it anyways. Here, right? Let's see. How can we do this? I don't know if this will work because the gradient vector. But this is if we can write the function as z is equal to. That's what this is, the gradient vector. So I don't think they do the gradient vector for a level set in 3 dimensions. But I think it's worth exploring the gradient for this. So We're not going to get to optimization today. Oh, bummer. All right, so maybe we can come up with an example after we take a look at some of these properties. So in this, all throughout this, these notes that I have that I'm going to share with you, I use a convention of little f to be a function from R2 to R. So that would be a z is equal to f of xy function. And then I use capital F as a function from R3 to R, which now is a four-dimensional type of function. Okay, so that's just a convention for this sheet. The gradient of little f is a two-dimensional vector, and I wrote it with i's and j's. The gradient for capital F is a three-dimensional vector, and both of these are evaluated at their corresponding x naught, y naught, or x naught, y naught, z naught points. Okay, so that's the definition of the gradient. All right, more importantly, the properties. Let's take the first two first. Again, little f and big F. So the gradient of little f is a direction in which the directional derivative of f is a maximum. We saw that. Remember, if you're walking up on a hill and you look at your compass, if you point your compass in the direction of the gradient and you walk towards that direction on that hill, you're going to be climbing the steepest direction. Okay? And we used to have a, I don't know if you guys know this, back in the day, we used to have a big hole in the middle of the quad, upper quad, where it just goes down, and that was before Building 9 was built. So I used to have a field trip there with my Calc 3 class, and we'd go stand on the hill, and I tell them to walk towards the gradient. So they have to walk towards the highest. Anyways, so that's the first property, is that the gradient is a direction in which is going to give you the fastest increase. Now, I put little f over here, but this could possibly work for big F as well. Remember that flying around? If the fly wants to go and feel the fastest increase in temperature, it's going to fly in the direction of the gradient. A second property we talked about, gradients are perpendicular to the level sets. So in two dimensions, it's perpendicular to a level curve. Okay, so this is flat in 2D. In three dimensions, we just proved today that the gradient is perpendicular to a level surface. Okay? So the gradient, remember, is a three-dimensional vector for a function like this with an input from R3. If your input is from 2 dimensions, then your gradient is a two-dimensional vector, so it should be perpendicular to a level curve, two-dimensional. All right, and then we just talked about the tangent planes. And then nice compact formula for tangent planes. If your function is a function z is equal to f of xy, then the normal vector is fx, fy, negative 1 for the z component. And then you can write that as your tangent plane equation, like the way we saw it the first time. And if you're talking about a level surface, then your normal vector is fx, fy, fz. Your normal vector is fx, fy, and fz. And then you can create your equation of the tangent plane this way. Okay? So the next page is dealing with directional derivatives. Here's a definition for directional derivatives, and here's some important facts about directional derivatives. A couple things that I did not go over. Are a couple of properties for the directional derivative. So here's a definition of the directional derivative, which I won't go over. But let's take a look at and highlight a couple of properties for the directional derivative. First, in the I and j directions, the directional derivative is just the partial derivatives. And we talked about that. The derivative of f in a direction perpendicular to this, the gradient, is 0. What's that mean? Back to the compass, and you're standing on the hill. You take a look at your compass, and it's pointing in the direction of the gradient. Right? Instead of walking in the direction of the gradient, if you walk in a direction that's perpendicular to the gradient, what's going to happen? You're walking along the tangent, you're not going to change in height. You're going to walk along the level curve, and so your height will not change. So the derivative of that along that direction will be 0 because there's no change in height. The function f increases most rapidly from any point going in the direction of the gradient. And the directional derivative in this case, if you were to compute it, the directional derivative is the magnitude of the gradient. Okay? So thinking about that might hurt your brain a little bit, but if you write that down, according to the definition of the directional derivative, if you let u be the gradient, of course you have to make it into a unit vector, and you do the computation, you'll see that that would simplify to this. Or the fastest decrease would be the opposite of that. Okay? So I'll let you think about that on your own. Okay, should we squeeze in another example? No. This is enough to deal with, right? All right, so I suggest that you play around with the 3D grapher. Pari suggested that you take a look at the gradient, being able to draw the gradient. We didn't do that in class, but you should mess around with that so you can see how the gradient looks like. Keep up with the homework. Over the break, I will work on the grades, and so hopefully by the time we get back, you'll see all your grades inputted up to whatever it is that we've gone up to with your homework scores and everything. Okay? All right, any other questions? Okay, have a good break.